Hello friends, and welcome to this video. And today we are going to discuss in this particular video the topic convergence of the LMS algorithm. So in the previous video we have already seen the details of the LMS algorithm standing for the least mean square algorithm here, and the advantages offered by the LMS algorithm for the practical issues over the earlier algorithm that we have learned, the steepest descent algorithm here. So while estimating the ensemble average, that can be the estimate of E of n, which is the error signal, the difference of the desired signal D of n with the input signal X of n that we have seen in the block schematic of the first video here, multiplied to the complex conjugate of the input signal X of n. So in estimating the ensemble average as the expected of the multiplication of E of n with complex conjugate of X of n here with 1 point sample average, the condition we have taken in the previous video of LMS algorithm. So the average can be denoted of E of n with the complex conjugate of X of n as denoted there also. The LMS algorithm here will replace the gradient step into the previous algorithm. The previous algorithm is the steepest descent algorithm. The gradient was for the zeta of n here. So the grad zeta of n was equal to minus the estimate of the product E of n with the complex conjugate of X of n. So this has been replaced by the estimate as it is always denoted with the help of cap over its head. We have del cap of zeta of n, that is equal to minus E of n into the complex conjugate of X of n here. So when this is accomplished here, the correction that is applied to W suffix n is generally not aligned with the direction of the steepest descent here. And since we have the gradient estimate to be unbiased here, we denote capital E of the estimate of the gradient denoted by del cap zeta of n, that is equal to minus of the estimate of E of n with the complex conjugate of X of n, to be denoted as delta zeta of n here. So that time the correction that is applied is on the average in the direction of the steepest descent here. Now with respect to certain observations that we can make for the LMS algorithm for a stationary process here, now we can have the consideration of the convergence of the LMS adaptive type of the filter here. Now since we have the usual notation W suffix n, the vector of the random variables here, the convergence of the LMS algorithm must be considered within a statistical framework. So therefore here we will start with one assumption that the requirement of the X of n, the input discrete time random signal, and the desired signal denoted by D of n are jointly wide sense stationary processes, and we shall have the determination when the coefficients W suffix n will converge into the mean to the W here. So here we denote limit n tends to infinity for the estimate of W suffix n, that is equal to simply W given in terms of the inverse of the autocorrelation matrix capital R suffix x multiplied by the cross correlation between the desired signal and the X of n input signal. So there it is, small r suffix dx here. Now when we can make one substitution from the previous equations shown for the algorithms LMS and the steepest descent here, the LMS coefficient update equation will be of the form W suffix n plus 1 is equal to W suffix n added by mu multiplied by the square bracket where we have D of n minus the transpose of W suffix n multiplied by X of n here, and further the square bracket is multiplied by the complex conjugate of X of n here. Now when we take the expected value, so that time for both the LHS and RHS we will have the new representation. So the expected value of w suffix n plus 1 is equal to the expected value of w suffix n added by mu multiplied by the expected value of d of n into the complex conjugate of x of n here, minus we have mu multiplied by the expected value of complex conjugate of x of n with the transpose of x of n into w suffix n. So as we focus on to the last term of this particular equation, it is not very easy to have the evaluation here, and that can be simplified considerably if we make the independent assumption. Independent assumption here we discuss. So the convergence of the algorithm is possible when we have the independent assumption. The assumption is as such: the data that is represented x of n and the LMS weight vector denoted by w suffix n are statistically independent. Now we shall focus on to the two properties associated to this particular current topic here. So let us have one property. This is: for jointly wide sense stationary processes, the LMS algorithm converges if the case is, or for the mean denoted mu greater than 0 but less than 2 divided by lambda max, and the independent assumption is also satisfied. Now there it is another property. Here we have the mean square error denoted by zeta of n converges to a steady state value of, here we have zeta of infinity in terms of zeta suffix mean added by zeta suffix ex of infinity. So here we have zeta suffix mean in multiplication to 1 upon 1 minus mu multiplied to the summation k is equal to 0 to p into the lambda suffix k divided by 2 minus mu into lambda suffix k, and the LMS algorithm is said to converge in the mean square if and only if the step size denoted by mu satisfy the two conditions here. The condition number 1 is that mu is greater than 0 but less than 2 divided by lambda max, whereas mu multiplied to the summation k is equal to 0 to p carried on to the ratio of lambda suffix k to that of 2 minus mu into lambda suffix k is less than 1. Now concerning the vergence of the mean square error, there it is one more parameter. The knowledge of this particular parameter can be essential to solve the problems based on to the LMS algorithm here. The factor, the term, you can say that it is the misadjustment denoted by the capital M here. It is basically the ratio of the steady state excess mean square error to the minimum mean square error, and here is the mathematical formulation for the same. Capital M is equal to zeta suffix ex of infinity divided by zeta suffix mean here. So here we conclude our topic, convergence of the LMS algorithm here. Thank you.